Hello everyone, and thank you for reviewing my assignment 2 project for CSE158R. In this presentation, I will walk through the predictive tasks we selected, the exploratory data analysis and pre-processing steps we performed on the Amazon Electronics Review dataset, the modeling approaches we implemented, the evaluation methods we used, and the short discussion of related work in this space. I will be focusing on the structure of my HTML notebook, which contains all the code, outputs, tables, and visualizations referenced in this presentation, so you can scroll through the notebook as I talk. My goal today is to clearly explain how I formulated the machine learning problem, how we worked with the dataset, what modeling choices we used, how we made them, and what the results mean for prior research. Let's start with section 1, the predictive task, evaluation, baselines, and validating. The predictive task we chose to focus on this project was rating prediction. The problem can be stated as follows. Given an Amazon review from electronics category, including the user ID, product ID, the review text, the review title, and whether the purchase was verified, useful boats, timestamps, and optional image metadata. The goal was to predict the star rating that the reviewer assigned on a 1 to 5 scale. This is a regression problem, since the output is a continuous value that we often treat as a numeric even though it's integer value. In our notebook, you will see that the dataset comes from a JSON-L file called electronics.json, which contains tens of millions of reviews entries. Each entry field has fields like rating, title, text, images, as in, parent, as in, user ID, timestamp, etc. Whether it was a verified purchase, and the number of helpful votes. For the evaluation metric, we use the mean squared error and root mean squared error. Root mean squared error is particularly appropriate because it penalizes large errors more heavily, and in rating prediction, being off by 2 stars is worse than being off by 1. We also check consistency, validity by evaluating performance across a held out validation split, temporal splits, and basic residual analysis. Now let's move on to the baselines. For the baselines, we use several standard ones. Global mean baseline, an item mean baseline, user mean baseline, and text-only baseline. All of these baselines are widely used in recommender systems and provide good anchors to show whether more complex models might actually improve performance. The task is directly relevant to this course because rating prediction was one of the primary tasks covered in lectures, particularly when discussing user item interaction matrices, collaboration fields, and hybrid models. This also sets up to compare more advanced models to simpler baselines. Now for section 2. In section 2, I'll talk through the exploratory data analysis section of the notebook. Starting with the dataset context, this dataset originates from Amazon large-scale review corpus. The electronics category contains review for thousands of consumer products such as headphones, cameras, cables, monitors, accessories, and other electronics. In this case, each row in the file corresponds to a single review written by a user. The dataset is originally stored in JSON lines format. This means that each line is its own JSON object. In the notebook, you will see that we load the dataset line into a pandas data frame. And because the dataset is quite large, we first load a sizable sample for exploratory analysis. Then we construct the full modeling dataset once pre-processing steps are established. In the notebook, you can see in the data frame head, as I scroll below, here in the data frame head, we can see that the first few rows, for example, include columns such as the rating, which goes to 1 to 5 star rating scale, the title, which includes a short summary of the review, the text, the full body review, the ASIN product identifier, the user ID, which refers to the reviewer ID, the timestamp in milliseconds, the helpful vote that designates the number of helpful votes the review has, and whether it's a verified purchase or not, as well as some images in some cases. The first step is cleaning the dataset in the notebook. You can see that when we drop the missing rows, you can see that when we drop the missing rows, for example, that lack rating or text, we convert the timestamps to Python, as you can see here, and we cast all variables to appropriate types. One important derivation we made was creating the column called word count, which we named as review length words. You can see these computation right here at this cell and below. This lets us analyze how long reviews tend to be and whether review length correlates with rating. From there, we created many plots. For example, we can see the first plot in the notebook. You can see a bar chart representing the distribution of star ratings across the dataset. As we hover over this plot, you can see that the distribution is heavily skewed toward the 4 and 5-star ratings. In fact, they represent nearly 80% of all the reviews. This is very typical for Amazon review data since consumers tend to provide more extreme reactions and many users only leave reviews when they feel very strongly towards a product. This ends up skewing this ends up skewing has skewing implications for modeling, which in particular encourages the uses of baselines like global mean and item means, which are naturally high. It also means that predicting a 5-star rating often yields a deceptively low root mean squared error unless we carefully check residual patterns. Now, we also created many plots, as you can see below. And for the sake of time, I will skip through them and just mention them. For example, rating distribution by verification status, rating frequency by verification status. These ones that analyze review length, for example, for verified and non-verified reviews, the verification rate, the verified purchase rate over time, and the rating distribution for verified versus non-verified. We can see review length versus rating. But the ones that we'll focus on right now is these KDE visualizations and violin plots. These plots represent the word counts across the ratings. This plot shows how the length of a review varies depending on whether the review is a 1, 2, 3, or 4 or 5 stars. As we discussed in the text of the notebook, 1 and 5-star reviews tend to be longer. And 3-star reviews are generally more concise. This makes intuitive sense because moderate reviews are often less expressive. This visual separation in density curves suggests that the text length contains some predictive signal. However, because there's still a lot of overlap between the distributions, review length is not that strong. It's not strong enough to function as a standalone predictor, but it does hint, though, that richer text features will help. The next plot that we will go in are time trends in rating. This one I thought was very interesting because we can see the average rating over time of all the reviews and how they have decreased. The average rating has sort of standardized over the years. The plot is aggregated monthly, and when we look at this plot, we can see seasonal variation. For example, ratings tend to dip slightly during major shopping seasons, which makes sense, possibly due to the higher expectations or maybe negative experience from high volume purchases. This makes it so that our choice to use a time-based validation split, preventing the model from learning from future data when predicting the past. Additionally, the timestamp field provides useful metadata since older products often receive different types of reviews than newer ones. In the plots below, we can see more of that seasonal trend that we talked about previously. Some other steps we took to prepare this data was lowercasing the review text, removing extremely long reviews to avoid undue influence, creating binary flags such as has images, and checking for duplicates, which there were almost none of them. Also, we ensured all numeric fields are properly typed. Before moving on to section 3, I will just scroll through the notebook to show some of the very interesting plots we made for this project. Let's move on to section 3. In this section, I'll describe the models we implemented, why we chose them, and the most important details behind how each of them works. For the modeling part, we built a total of 6 models: a global mean predictor, a user and item mean baselines, a formal bias model, a matrix factorization model, a TF-IDF ridge regression model, and finally, a weighted ensemble that combines all the elements of how the other works. I'll walk through what each model is doing and then tie them to the results we observe in the evaluation section. For starters, the first model, the global mean model, which can be seen right here, is the simplest possible baseline. It predicts every rating as the average rating in the training set. In this data set, that value is a little above 5 stars, 4.25 to be exact. The purpose of this model isn't to perform well. It basically is to give us for a baseline, a reference point to measure improvement. As expected, its test RMSE, or root mean square error, is the worst out of all models at 1.3293. This gives us a starting benchmark that every meaningful model should improve on. Moving on, we implemented the user mean item mean model. This is a combined user plus item mean baseline. The idea here is to see whether personalization alone, without any advanced modeling, is sufficient to reduce error. User mean predicts a user average historical rating. Item mean predicts the average rating of the item, and the combined approach averages both. These are useful because they add structure and some uses are because some uses are harsh, some are lenient, and some items are consistently loved or disliked. However, in this dataset, these baselines do not outperform the global mean. User mean gives a root mean squared error of 1.37. Item mean gives a root mean squared error of 1.37 as well, and the combined version gives 1.3748. The takeaway here is that in any sparse datasets with many infrequent users and products, simple averages are unreliable. This motivates using better collaborative methods. This leads us into the third model. The third model is a bias model. This is a classic recommender systems model that predicts ratings using 3 components. First, a global mean. Second, a user-specific bias. And finally, an item-specific bias. Unlike the simple averages, these biases are learned with regularization. This prevents extreme values for users or items with very few reviews. The model can be described as lightweight, interpretable, and often forms the backbone of collaborative filtering systems. In our notebook, the bias model performs noticeably better than any baseline, reaching a root mean square error of 1.2837. That's a substantial improvement considering how simple the model is. It shows that there are systematic rating tendencies among user and items, but they must be learned in a controlled way rather than simply averaged. From here, we move on to the expressive collaborative model, which is the matrix factorization, sorry. This model assigns each user and each item a latent vector of learned embeddings. The predicted rating is the dot product of the user and item vectors, optionally with biases added. The model is capable of representing complex user-item interactions. For example, a user who prefers certain brands or items that appeal to similar types of reviews. We trained the model with a 20-dimensional matrix factorization model using stochastic gradient descent with regularization and a fixed learning rate. Although the model shows excellent training performance, the training root mean squared error drops below the 1. We observe a test root mean square error of 1.2827, which is actually extremely close to the bias model. This means the model learns more structure but doesn't generalize much better. Sparse users and items make it hard for matrix factorization to fully capture preference and without textual information. The model, we can say, generally lacks descriptive features for products. The next model is the strongest single model in the entire project, the TF-IDF plus ridge regression. Here we ignore the user ID and item ID entirely, and instead treat the review text as the main predictor. We convert every review into a vector of weighted worth frequencies using TF-IDF, and then learn as rich regression model to map these word patterns to a numeric rating. The model leverages sentiment clues, descriptive language, and product-specific terminology that is invisible to collaborative models. The result then ends up reflecting that. The test root mean square error drops to a 0.93, which is a huge improvement over collaborative approaches. The model is also very accurate in classification, and when ratings are rounded, is 52.86, the highest among all standalone models. These numbers show that in the electronics dataset, the strongest signal of rating is embedded in the text itself. People use extremely descriptive wording that directly correlates with rating sentiment. Finally, we constructed a weighted ensemble of three major models: the bias model, the matrix factorization, and the TF-IDF plus ridge regression. The weights are determined inversely proportional to validation root mean square error, meaning better models get higher weight. The final weights came out to be 41 text model, 29% matrix factorization, and 29% bias model. We might expect the ensemble to outperform every individual model, and it does outperform the collaborative ones, but it does not beat the TF-IDF model alone. The ensemble achieves a test root mean square error of 1.0574, which is good but not close to the TF-IDF performance. The reason is straightforward. The text model is dramatically stronger, so mixing weaker models into it actually dilutes it. If we use the nonlinear or learned blending technique, results might improve, but with the simple averaging, TF-IDF model remains the strongest component. This concludes the modeling section. 6 models, each progressively more expressive, with clear performance difference that we'll now interpret in section 4. In this section, I'll interpret the results of the model I just described and explain what we learned from comparing them. Starting with the baseline results, the global mean produced an RMSE of 1.32, which serves as our worst case reasonable scenario, as you can see here. The user and item averages performed even worse, showing that naive personalization is not reliable in this dataset. The bias model, however, substantially reduced error to 1.2837, demonstrating that systematic user and item tendencies exist and are helpful when regularized. Matrix factorization surprisingly only slightly improved over the bias model with an root mean square error of 1.2827. In many recommendation datasets, matrix factorization offers major gains, so seeing it perform similarly to the bias model is informative. It suggests that the electronics dataset suffers from sparsity. This means that many users and products simply do not have enough overlapping interactions for latent factors to be learned effectively. The training root mean square error for matrix factorization is extremely low, nearly 0.96, while the test root mean square error is much higher. This gap signals overfitting. The model memorizes training performance that do not generalize well. As mentioned earlier, our strongest model is clearly the TF-IDF ridge regression model, with a test root mean square error of 0.9345. This improvement of almost 30% over the global mean baseline demonstrates that textual sentiment and product description hold the most predictive power. When a user writes a review, they naturally express dissatisfaction through their language, and that signal can be learned much more effectively than latent user-item relationships. The ensemble model shows an important results. Combining collaborative and text models yields a root mean squared error of 1.0574, which is solid but not better than the text model alone. This tells us that two things. First, the TF-IDF model is carrying almost all the predictive weight. Second, simple averaging is not powerful enough to exploit the complementary structure of the models. A more advanced stacking method or a neural hybrid model might improve over TF-IDF alone. Finally, we validated the models through residual analysis and stratified performance checks. Errors were the highest Errors were highest for extreme ratings, 1-star and 5-star rating reviews. Because these represent emotional or outlier cases that are harder to match precisely, collaborative models suffer heavily on cold start users and items, but text-based predictions remain stronger whenever review text exists. Overall, the evaluation shows a clear conclusion. Text dominates collaborative structure in this dataset, and while collaborative filtering can help, it cannot match the expressiveness of linguistic sentiment and review detail. Here we can see some plots that tell us that TF-IDF regression model is the best one, and we can also see how each model performs on graphics that make it more visual. These plots further highlight that TF-IDF ridge regression model is the more precise and tells us the most about the dataset when we're trying to predict the rating of the product. To conclude, I'll discuss how the dataset and modeling approaches relate to prior work in recommender systems. The Amazon product reviews dataset, especially subsets like the electronics, has been extensively studied in literature for over a decade. It has been used for tasks such as rating prediction, sentiment classification, helpfulness prediction, aspect extraction, and building hybrid recommender systems that incorporate text. Early research showed that Amazon reviews contain rich user-generated content that can be used to understand preference beyond simple ratings. Historically, two families of models have dominated rating prediction: collaborative filtering models and text-based models. Classic collaborative approaches include the bias model and matrix factorization, which we touched on earlier, which were actually foundational for a Netflix recommender systems. Many papers demonstrated that matrix factorization significantly outperforms simple baselines on dense datasets. However, more recent work, especially on Amazon reviews, has shown that when text is available, content-based models can achieve much stronger performance because they capture sentiment and nuance that numerical ratings alone cannot represent. Our results are consistent with this trend. The TF-IDF ridge regression model outperforming matrix factorization matches what has been reported in prior research. When text is rich, traditional collaborative filtering struggles to compete. More modern neural models such as DeepCon, NN, NAR, and BERT-based architectures outperform TF-IDF models by learning deeper semantic representations of reviews. These systems typically achieve root mean squared error improvements beyond what classical models can achieve, but they come at the cost of significantly more computational requirements. Finally, the idea of combining collaborative and content features is also well explored in hybrid models. Many studies report that weighted or stacked combinations of text and interaction models can outperform either alone. In our case, the ensemble did not beat the TF-IDF models, but this most likely reflects the simplicity of the ensemble method rather than the absence of complementary signals. Overall, the results of the project align well with existing research. Text-based models are particularly strong on Amazon reviews. Collaborative models help, but are more limited by sparsity, and hybrid models hold the most promise when implemented with modern techniques. Thank you for listening.